So how in the world do you teach a machine to think? I'm not talking about some sci-fi super intelligent robot. I mean, at the most basic, fundamental level, how does a computer even begin to understand a simple logical idea? Well, that's exactly what we're going to break down today, the absolute building blocks of AI reasoning. Let's jump right in. Okay, so take a look at this question. For you and me, if it's raining, then the roads are wet. Is just obvious, right? It's a no-brainer. But for a machine, that's actually a massive challenge. The real problem we're solving here is how to translate that simple, human piece of logic into a language that a computer can actually understand and work with. To get there, our first stop is figuring out how to teach a machine to reason in the first place, because before an AI can make any kind of decision, it needs one thing above all else, and that's knowledge. And here's the thing, that knowledge can't just be a jumbled mess. You can't just dump a giant cloud of facts into a computer and expect it to work. It's totally useless unless it's structured and organized in a very specific way. That's the only way a machine can read it, interpret it, and finally make some intelligent decisions. So how do we build that structure? Well, we start with the simplest, most fundamental method there is. It's called propositional logic. Now, don't let the fancy name fool you. A proposition is really just any statement or sentence. Think of this as the absolute ground floor. It's like the ABCs we're going to use to build the entire language of machine logic. Now, what's so wild about this is that this entire incredibly powerful system is built on top of one single, unbreakable rule. It is shockingly simple, but it is the foundation for absolutely everything else we're going to talk about. And here it is. This is the rule. Every single statement, every proposition can only be one of two things. It is either true or it is false. That's it. There's no in between, no maybe, no kinda. This super strict black and white distinction is exactly what a machine needs to operate without any confusion or ambiguity. And this slide right here shows that rule in action. On the left, we've got clear-cut cases. New Delhi is the capital of India. That's a proposition because it is definitively true. And hey, 2 + 1 = 4 is also a proposition because it's definitively false. But now look at the right side. Some students are intelligent. Why isn't that a proposition? Because it's ambiguous. We can't give it a definite true or false. It's subjective, it depends on your definition, and this kind of logic system demands absolute certainty. So we've got our one big rule. Everything is either true or false. Got it? Now let's look at the grammar. How do we take these simple little statements and start building them into more complex, more meaningful ideas? Well, it turns out propositions come in two main flavors. First, you've got your atomic propositions. These are just single, simple ideas. Think of them like a single Lego brick. The sky is blue. Then you have complex propositions. This is just what happens when you take two or more of those atomic Lego bricks and snap them together to build something bigger. The real question is, what do we use to snap them together? We connect them using these 5 little tools. They're called logical connectives. And as you can see in the table, they're basically just the super precise logical versions of words we use every single day. Not, and, or, if then, and if and only if. This is the glue that lets us build real arguments. Let's start with conjunction. That's the fancy term for and. And this example is just perfect. Please like my video and subscribe to my channel. For that entire statement to be considered true, what has to happen? Well, both things have to happen. If you only do one, then sorry, the combined statement is logically false. Now let's flip to disjunction, which is just the logical or. You should eat or watch TV. With an or statement, things are a lot more flexible. The whole thing is true as long as at least one of the parts is true. So if you're eating, it's true. If you're watching TV, it's true. In formal logic, it's even true if you're doing both at the same time. The only way it's false is if you're doing neither. Okay, but now we get to the real powerhouse of reasoning, implication. You probably know it as if-then. This is what connects a condition, we'll call it P, to a consequence, Q. And look at that, it's our original example. If there is rain, P, then the roads are wet, Q. This little arrow is the heart of logical deduction. All right, hang with me here because this slide is where if-then logic gets a little weird, but it's so important. The first 2 rows, easy. If it rains and the roads are wet, our rule holds up, it's true. If it rains and the roads are dry, our rule is broken, it's false. But now, look at that 3rd row. It does not rain, but the roads are wet. Is our original statement false? Nope. Surprisingly, it's still considered true. Why? Because our rule only made a promise about what happens if it rains. Since it didn't rain, the promise was never broken. Maybe a fire hydrant burst or a street cleaner came by. The rule wasn't violated, so logically it still stands. That's a huge concept in formal logic. Okay, so we've got our one big rule, true or false. We've got our little atomic building blocks, and we've got our connectives to stick them all together. So let's do the final payoff. Let's take a real, messy English sentence and translate it into the clean, crisp language an AI can actually use. Here is our challenge. You can access the internet from campus only if you are a CSE student or you are not a freshman. Now, we can read that and figure it out, but to a machine, that's just a jumble of words. Let's use the tools we've just learned to clean this up. So here's the 4-step process. First, we act like detectives and pull out all the simple statements, the atomic propositions, and we give them variable names. P is you can access the internet. Q is you are a CSE student. R is you are a freshman. Easy enough? Next, we find our logical keywords. Only if becomes our if-then arrow, or becomes our V symbol, and not becomes that little negation symbol. And for the final step, we just assemble the puzzle pieces. P implies Q or not R. And look at that. We took that long, kind of clunky English sentence, and we boiled it down into something that is clean, precise, and completely unambiguous. This final expression right here, this is a set of instructions an AI agent can actually read, understand, and use to make a decision. We've successfully translated human language into machine logic. Propositional logic is incredibly powerful. It gives AI a solid foundation, a way to reason about the world in these strict, black and white terms. But in learning how it works, we also see its biggest limitation. What happens when things aren't just true or false? I mean, think about how we talk. We use words like maybe, sometimes, probably, a little bit. The real world is full of gray area. So how do you teach a machine to handle that kind of uncertainty? Well, that's the next great challenge in the world of AI reasoning.